example we have for the helical gear design, and this question actually is an example we have in the textbook. Here I just did some of the modification that's going to actually fix some of the mistakes, and also I extended the solution so all the steps is going to be more clear for you. So in this question we have a pair of helical gears for the milling machine. Drive is going to be transmit a 48.47 kilowatt or 65 horsepower with a pinion speed of 3,440 RPM and a gear speed of 1,100 RPM. The power is from electrical motor. Design the gears. So from the question we can say that the given details where the driver is electrical motor, the driven is milling machine, and the power is 65 horsepower, and the pinion speed is 3,450 RPM, and the gear speed is 1,100 RPM. Find the helical gear for this example. So the first step is going to be by finding the design power, because you remember that the power we have here is the actual power. We need to design for more safety factor, so again to multiply it by what we call it the overload factor. So we start with the calculating of the design power. We look for the overload factor KO. So here we say we are going to use, unlike the previous example when we use the light shock against the moderate shock, we are going to use a uniform power source and moderate shock in the driven machine. So the KO is going to be equal to 1.5, and thus the design power is going to be 1.5 multiplied by 65, and this will give me 97.5 horsepower. So in this case, usually the steel gears are going to be the option, so we're going to use them and run the design accordingly. So we're going to start with the trial size for the pinion. We will try a normal diametral pitch value of 12. We're going to have 24 teeth like we did last time for the pinion, the helix angle of 15 degree, a normal pressure angle of 20 degree, and the quality number of 8. So by using these trial sizes, we are going to go and calculate the basic calculation for the helical gears, which including the computing of the transverse diametral pitch value, the axial pitch value, the transverse pressure angle, and the pitch diameter. So everything actually has been explained earlier, so no need to go through them in very much details. You can see here that the PD value is given, the PX value equation is given, the phi, the DP, and the F. So we start to get the PD value to be 11.59. The PX or the axial pitch is going to be 1.012 inches, and the phi value is going to be 20.65. The DP or the diametral pitch value is going to be 2.071 inches, and the face is going to be 2 times the PX, and this will give me a 2 times 1.012, and this will give me 2.024 inches. That's for the nominal face width. To get more accurate calculations, we're going to use the value for the face to be 2.25 inches. Okay, so this is more convenient value. We can find a standard gears for the same dimension. It's much easier than taking 2 inches because we cannot get the 2.024 inches. Now step number 4 is going to be to determine the tooth number in the gear, because now we have 24 for the pinion. So we start to calculate the pitch line speed and the transmitted load. First we're going to go with the speed. It's going to be pi multiplied by the diameter, dp actually here, multiplied by the rpm divided by 12. By the calculation we will find that the value for the velocity for the pitch line is going to be equal to 1,871 feet per minute. For the tangential force, we know the horsepower is 65, and the VT is calculated as 1,871. So we will find that the tangential load is going to be equal to 1,146 pounds, which is equal to 5.1 kilonewton. Now we do the calculation for the number of the teeth on the gear. Basically, we're going to use the velocity ratio, or the VR. So for the velocity ratio, it's going to be number of the teeth of the gear divided by the number of the teeth on the pinion, and this will be equal to the RPM on the pinion divided by the RPM on the gear. And the ratio is going to be 3.14, and we know that the number of the teeth on the pinion was 24, so we're going to have 75 teeth, which is an integral value. Just simply we're going to take it up or down according to your choose. Now from that, that's it. We need to calculate the stresses. So we start first by determining the factors for the stress calculations. So to fulfill the requirements of the equation 916, we must now determine we need to find all the factors enabled to be able to calculate the bending stress. So now the PD is known, WT is known, F is known, we need to find the J, KO is known, KS, KM, KB, and KV. So we're going to start to do that. I'm going to show you most of the calculation, which is just simply repeated from this per gear. So we start with the value for the J. So geometry factor, or the JP, is going to be found by using the chart the 10.5, and this is for the 15-degree helical angle. If I'm going to use, for normal pressure angle, 45. So if I'm going to use the 20 or 25, definitely you're going to use a different figures. This can be 10.6, I don't remember. Anyway, so here we have the curves. We need to find what we know. We know that the helix angle is given as we suggested to be 15, and I'm going to go to number of the teeth. We're doing that for the pinion, so simply I can say that number of these is going to be 24. Is something in between the 20 and the 30. Intersect that, going to the left, and I get the value here directly. And we choose it to be something like 0.48. So of course you can get less. If I'm going to pull this one downward, then I'm going to get something like 0.46, for example. Okay, it doesn't matter. It's not going to make a big difference, but anyway, we will start with the value that's found by the example itself. Now we know the JP. Next step is going to be finding the KM. So to find the KM, first we need to find the pinion proportion factor, or the CPF. Now that's the same diagram that we had last time for the spur gear. They're showing the same thing, and simply we're going to go and find some of the parameters we know. For us, we know that the face width has been chosen to be 2.25. and the diameter of the pitch value was 2.071, so the ratio of the F to the DP is going to be equal to 1.09. So this will be more than 1, less than 15, so we can use this equation. If I get to just using the chart, I'm using the 1 for the F over DP, that's the closest one. Little bit above is going to be 1.1, so we're going to go through this line here. 2.25 for the face width, intersecting, and again to get the value something as close as possible to a 1, but it's not 1. So when we did the calculation, I found that the number is going to be 0.099. The question, the example in the book, actually it just give the answer without doing the steps of the calculation. Now, next step, we still need to find the value for the CMA. So for the CMA, once again, we're going to use the chart 913, that following this one, okay? And in that case, we're using the commercial enclosed gear unit as we done last time. So the equation is going to be that one. Once again, the F is 2.25, so simply I can, oh sorry, that's wrong here. What I can do is 2.25 here, and I'm going to intersect it with this curve line, and then I'm going to get the value to be roughly 0.16, because this is 0.15, this is 0.2, so it should be something like the first fifth of that square. If I'm going to do the calculation with the value of the f to be 2.25, I will get the answer to be 0.162, which is very, very accurate. Now, I had the CPF, I know the CMA, so I can calculate the KM. By putting that in the equation, I will get the value for the Km to be equal to 1.26. Now we need to find what will be, of course, that's what we call the load distribution factor. Now we need to find the size factor or the Ks, and we can do that from the table 9.2, and the Ks for when the module or the diameter pitch value is more than 5. Okay, my diameter pitch is more than 5, we got 11.25. So we're going to choose the value for the Ks to be equal to 1. Now we determined the Ks, we found the load distribution factor, and we got the rim thickness factor. We did that last time for a solid gear to be equal to 1, and then determine the dynamic factor Kv, which is going to be equal to 1.26, and that's for the value for the AV to be equal to 8. Now how did we got the value for the quality factor? If I'm going to go to this table, you can see that the speed range between 800 to 2000 feet per minute, we're going to get the quality number to be A8. So I go to the A8, and the velocity is 1871, intersecting between them, and we get the value of the KV to be here, which is more than 1.25, and a little bit, well, we can say 1.25, 1.26, 1.27, whatever the value, I choose to be 1.26. The one in the example in the book is 1.35. That's the correct one. Now we continue by having the all the K's has been calculated, the J has been calculated, the F is known, the power, the design power is known, so we can calculate the bending stress. So by putting all these parameters in, I will find that the value to be 29,287 psi, which is equal to 201.93 megapascal. So now I know what the value of the bending stress. I can find what will be the required toughness or hardness for the gear. So the hardness bending for the grade 1 of the steel, we are going to choose that by simply finding what will be the intersection. So our value for the stress is about 200 or 29,000. So we're going to have this line is only going to be intersecting with the grade 1, and thus I will find that the value of the hardness required is going to be 220. That's for the Brenner test. So yep, we got that. We are going to move forward and calculate the rest. Now we need to find so actually we need to find first the CP in order to calculate the rest of the work. So the CP value for table 9.7, like we did last time, for the two gears, both made of steel. So steel with the steel, the CP value is going to be 2,300. Now we are going to calculate the value for the I, and we can find that from the table 10.1. And you can see here that our gear has 75 teeth, our pinion 24 teeth. If I'm going to check here in the table, I don't have this value. I have for the gear, I have 55 and 135, and for the pinion, I have 21 and 26. So I can find by the interpolation the value in between for the 24, and then the value in between for the 75 between these two values. Okay, so that's it, and I'm going to now jump to find the rest. So the I has been found to be 0.202, which is somewhere here. Okay, 0.202. Now we're going to find the value for the contact stress, because now I know the CP and I know the I value, and I know all the parameters that are given to us in the contact stress equation. So once again, we are going to apply the calculation, and we will find that the value to be equal to, oh, sorry, I should show you that earlier. Yep, so the value is going to be equal to 123,845 psi, which is equal to 853.88 megapascal. Now I encourage you to do the calculation for this step yourself and double check your answer. Now once again, we can check the hardness for the steel by using the contact stress, and we're going to compare which one is going to be the governing stress. From pre-judgment, I can tell that the previous one was 200 megapascal and this one is 853. So definitely the contact stress is going to be the governing stress for these gears. So we're going to choose the material according to, the stress according to that type of, that amount of the stress. So we're going to have the value to be 850. So we are going to be at this stage, okay, or it's going to be 120, almost 124. So just a little bit less than the 125. We intersected with the grade 1, and we're going to find that the hardness is going to be about 292 or 290. Or if I'm going to use the value for the grade 2, and the hardness is going to be around 252. Okay, so we're going to keep the 292. I can use the steel type 5150 oil quench tempered with 1000 at 1000 degree, that have the HV value of 321, which is more than the one we found by calculations. So now once again, if I'm going to talk about which stress is going to be the governing stress, the highest is the one. So it's obvious that the contact stress is going to be the governance this design. And let's just adjust this solution for higher reliability and to account for the expected number of the cycle operations. So for some certain design decisions should be made. And for example, we're going to consider the following steps for the decisions. So the suggested design decisions are going to be, for the reliability, we're going to take it as 1 in 10,000, as we mentioned last week. So the reliability factor is going to be 1.25, that's from the table 911. And design life, we're going to design for a life of 2,000 hours of the life, as suggested in the table 912 for the multi-purposes gearing. And then by using the equation 927, we can compute the number of the cycles of the loading. And for the pinion, with the rotating at 3,450 revolution per minute, with one cycle of the loading per revolution, we're going to find that the number of the cycles for the life is going to be 2.1 multiplied by 10 up to the power 9 cycles. So now we can choose the material according to what we got earlier, and let's use the NC. We are going to use the figure 922. We'll find that the value for the ZN to be 0.89. Okay, so we did that for the spur gear. We can go back to the video of the spur gear and find how we use the chart to find the value for the ZN, and also it can be calculated. So unusual conditions seems to be exist for this application beyond those already considered in the various K factors, and therefore we're going to use a service factor of 1. Now we can use the equation 927 to apply these factors, and we're going to calculate the allowable stress, allowable contact stress. So simply is going to be the SF multiplied by the KR divided by the ZNP multiplied by the value of the contact stress that we calculated earlier, and we are going to have that the allowable contact stress is going to be equal to 1,200 megapascal. So remember that the previous one was 858, I think. So now we can simply use the table 99 that indicates that the grade 1 is steel, case hardened by the colorizing will be a suitable one, because you can see that the allowable bending stress for it is going to be within the range. We got 200, this one had 379, and for the allowable contact stress we got here 1200. For the type of the carburized and case hardened steel, it's going to be 1241. Now, with these conditions, we try to check this if the steel is going to be suitable for us. So we are going to go to the appendix 5. We are going to show that on next page, and we are going to specify that the AISI 4320, the soaked oil quenched tempered 450 degree, having the case hardness of the 59 and the core hardness of 415. And this should be satisfactory for both the bending and the pitting resistance, and both pinion and the gear should be made of this material. So that's what we got here. Okay, so this is I just brought the bending stress and the allowable contact stress, and if I'm going to check it to here, once again, as I told you, that we are going to be within that range. Okay, so finally, we check in the appendix 5. That's the steel we are looking at. This is tensile strength, and this is yield strength. So both values are going to be harder than the one we need. And also for the case hardening, we get 62. For the Brinell hardness, HV value is 429. In the previous cases, we got the maximum to be 290. So this will be more than satisfactory for us, and we can choose the material to make the gear and the pinion. So thank you very much, and if you have any question, just send us an email or contact us through the Teams, and we're going to be more than happy to answer your questions.